In our previous session, we had discussed about lateral stability. Let us start off with directional stability in this session. Directional stability is on the vertical axis due to the vertical stabilizer and fuselage. To be directionally stable, an aircraft must have more surface area behind the center of gravity than in front, thus acts like a wing. When the aircraft yaws, the vertical stabilizer creates lift in restoring direction and sides of the fuselage offer a surface for the wind to push against it. Directional stability is improved by a sweep back wing. When yawing, the wing moving forward has large effective area, hence need more drag to push it back. If the aeroplane wing drops, it will tend to yaw into the low wing and the dihedral and sweep back will combine to return the wing to equal level. Directional or weathercock stability is concerned with the static stability of the aeroplane above the z-axis. Just as in case of longitudinal static stability, it is desirable that aeroplane also tend to return to an equilibrium condition when subjected to some form of yawing disturbance. Yawing moment coefficient versus side slip angle beta for two aeroplane configuration is shown in the table here. To have a static directional stability, the aeroplane must develop a yawing moment that will restore the aeroplane to its equilibrium state. Assume that both aeroplanes are disturbed from their equilibrium condition, so that the aeroplane are flying with a positive side slip angle beta. Aeroplane 1 will develop a restoring moment that will tend to rotate the aeroplane back to its equilibrium condition, that is a zero side slip angle. Aeroplane 2 will develop a yawing moment that will tend to increase the side slip angle. Examining these two curves, we see that to have a static directional stability, the slope of the yawing moment curve must be positive. Note that an aeroplane possessing static directional stability will always point into the relative wind, hence the name weathercocking stability. The Dutch roll mode is a classical damped oscillation in yaw about the z-axis of the aircraft, which couples into roll and to a lesser extent into side slip. The motion it describes is therefore a complex interaction between all the three lateral directional degree of freedom. Fundamentally, the Dutch roll mode is the lateral directional equivalent of the longitudinal short period mode. Since the moment of inertia in pitch and yaw are of similar magnitude, the frequency of the Dutch roll mode and the longitudinal short period mode are of similar order. However, the fin is generally less effective than the tail plane as a damper, and the damping of Dutch roll mode is often inadequate. The Dutch roll mode is also called so because the motion of the aeroplane following its excitation is said to be resembling the rhythmical flowing motion of a Dutch skater on a frozen canal. One cycle of a typical Dutch rolling motion is shown in the figure here. The physical situation applying in a Dutch roll disturbance can be appreciated by imagining that an aircraft is restrained in yaw by a torsional spring acting about the yaw axis Z. The spring stiffness being aerodynamic and determined largely by the fin. Thus, in straight, level trimmed equilibrium flight, disturbance in yaw causes the aerodynamic spring to produce a restoring yawing moment which results in classical oscillatory motion called the Dutch roll. Whenever the wing is disturbed from level trim, the aeroplane, left to its own device, slips sideways in the direction of a low wing. Thus, the oscillatory rolling moment leads to some oscillatory side-slipping motion in Dutch rolling motion, although the side-slip velocity is generally small. The ratio of peak roll to peak yaw is usually less than 1 and is usually associated with the stable Dutch roll mode. However, when the ratio is greater than 1, an unstable Dutch roll mode is more likely. I hope you would have understood all the sessions about the stability of an aircraft. Thank you.